Okay, we're at 4:44, so I guess I didn't really come in late by too many seconds, if at all. I do not have any papers graded. As I've said to three of you, at least I was up in Denver and had appointments yesterday too. I'm healthy though, at least. I had a physical, I had a dermatology appointment yesterday. They sprayed pre-cancer on my face, to remove something, which I've had done before, so I'll get a sore spot, and then new skin will reappear. So, but what I have done for class is get ready for lecture, and I also am getting ready for the demo of the final project. So, and since my tablet was rebooted on me, let's just go take a look at Slack, because last night I realized I had posted the final project, but I posted the wrong file. So you'll see this file deleted for the protecting of the innocent. If anybody downloaded it, don't save it unless you want to have another file that's similar, but it's this one that I put up here that is the correct one. It's the one that I'm going to demo right now, as a matter of fact. So it's a 500 meg download. It's big. If you work in digital signal processing for radio communications, as in software-defined radio, things add up fast. If you're sampling at megasample per second rates and you're getting complex samples, it builds up fast. And I wanted you to have a long file so you'll be able to listen to a long segment of the capture that I made. If this is a problem for anybody, just let me know. I can shorten this down, but I'd like you to be able to have this 500 meg. So, has anybody who still has to download it? You have or have not? I have not. Okay. John, you have, I'm guessing. Fine? Yep. Okay. So we're going to take a look at that first. Our topics will be, for tonight, will be the structures, which is more or less the network analysis side of digital signal processing. So we'll get into that, but I'm going to have to reboot now I did not reboot it. I started the Jupyter Notebook, so let's just see if that came up where I'd left it. It should. It's just that I'll have to rerun everything. So first off, though, I do have the project in here. So we'll talk about the project. This project is by no means comparable to the first project. The first project is a lot of nitty-gritty detail, and I admit that. It's going to take me a long time to wade through it all to grade it for just 3 projects. This is much, much different. Most of the code is written. You have to reconfigure some things and then go through and do the exercises, but it's not nearly as involved. The 2 projects together, though, will form your project grade, and that number will be available when we come to class next week. I may have it done earlier when I get the grading that's on the table done. So computer projects nominally total 20% of the final, and the final totals 25%. And the homework stays as it is right now, and exams 1 and 2 stay as they are. That was in the original syllabus. But the second option is computer projects can total 15%, the final 30%, and homework and exams, of course, stay the same. Most people will probably take by automation, because remember I told you my spreadsheet's just going to optimize. It's going to take whichever of these 2 options works the best for you. But I've explained that the first night of class, but I'm just reiterating on that. Everybody's turned in the project, so that's a done deal. The second project I know is going to be much easier to do. It's more qualitative than it is quantitative. You will turn in some zip files of audio that you've demodulated from the capture. You're going to be building this channelizer receiver. And before I forget about it, I did this capture last year. I tried to make a new one that I thought I could do better on, and I just gave up messing around with it. I don't know about you guys, but I mess around with my electronics get out my software-defined radio, strung out a long wire antenna, and other such things. And then at the end of the day, I throw in the towel and don't finish it. Do you ever find yourself setting out to do some quality time on schoolwork and then things just sort of deteriorate and you end up not making progress like you hope to do? Time is very valuable, but sometimes the time you spend learning through failures is valuable in the end, but at the time, it definitely doesn't seem like you can be accountable. And I hit a string of things. I mean, I have too many computers, so updating, maintaining software, stuff like that ends up taking too much time probably. I should probably quit and not have so many computers because it's a lot of work to keep them all running. So, but before I forget, when you demodulate the audio, and I'll talk a little bit about talk radio, but I'll just say this. Talk radio is what AM broadcasting is doing predominantly. They do sports, but talk radio is probably one of the main things that happen. There's a few music AM radio stations because you can travel across the country great distances and stay locked on an AM radio station for a very long time if it's a clear channel station, and I'll explain that too. But because talk radio has a lot of things going on with it, particularly right conservative movement and just very hardcore stuff. Sometimes, and I know in this capture there's stuff that's a little bit crude sounding. It's not FCC unacceptable, but it's not something that I put into the program. It's what I captured. And if you hear something, you know, it is what it is. And if you ever get to the point where you like listening to talk radio, and does anybody do that right now? Maybe you like listening to it. Some people listen to it 24 hours a day. There's always talk going on. I mean, I hear some construction workers or people in my neighborhood, like road work or something, they've got it playing. You can hear it when you walk past with your dogs or something. It's like, you guys listen to this all day long. But it's just the nature of it. I know another segment is a football thing, which we'll listen to because it was a station up in Denver that I think, I'm not positive, or maybe it's in the Springs. But at any rate, this topic is pretty interesting. It's called a channelizer, and somebody just left me a voicemail. The channelizer has the capability then to take an entire band of frequencies and process them through in parallel. So normally when you're listening to a radio, you tune into the radio station you want to listen to, but suppose you were somebody wanting to gather intelligence about what was going on, you would want to parallel process and have all these threads or streams coming into your device, so you'd make sure you would not miss anything because you'd analyze them offline or just analyze them with a massive bank of computers. So, and that's what we're doing here. We are doing it offline though, because the capture was made, but now we're going to demodulate and recover AM broadcast stations. So AM radio runs from 470 to 1670 kilohertz. That sounds like audio, but it's not, right? We only hear up to about 15 kilohertz. But this was a fundamental radio broadcast back in the beginning of radio. And AM radio is still in existence. There's a number of stations in the Springs, in Denver, and all across the country. There's 120 channels, and they're spaced every 10 kilohertz across this band from 470 to 1670. I don't listen to more than one station at a time, but you could concurrently, you could actually set up the playback so you could have in the right channel one station and left channel the other. You know, you could at least multi-process two channels. So there's a zip, and the zip just has the sample notebook that we're going to go through. It has some graphics that show up in the notebook. And then you mate that together with this document here and the big, huge SDR file, and then that's all you need to do it. So this is what the channelizer function, which is in SIG-Sys module. Last year it was not. It was a standalone, and then I got it integrated. So this is the interface to the function. Those are all the inputs that we use. And this block diagram depicts what's going on. So I want to walk through this. A stream of samples comes in, and the samples come in as subframes, and it has to do with the FFT-based processing. I'll explain that tonight, but next week when we talk about the FFT, you'll understand that an FFT is if it's going to be used for streaming data processing, it's a frame-based processor, because an FFT has a fixed length that FFTs, and it can inverse FFT, and then you have to roll in another frame. So we have subframes that are of length n FFT2, and this will make more sense when you see the next block diagram. So this box then, the way I've drawn the block diagram, is going to see a spectrum of signals, in our case AM radio stations, but it could be anything, and it's going to operate on that, and it's going to break it out into individual subbands. So the subbands will correspond to, say, channel S1 would come out, subband K is equal to 0, and so on down the line. There'll be gaps in there, but it's covering a whole range of spectra, and it's assuming that everything can be regularly chunked up into subbands, like for broadcasting. FM radio would be subband processed as well. I could have done a capture of that, but honestly, I thought this was more interesting myself. The idea is that we then want to filter to isolate, and that's what the channelizing terminology is. We're going to channelize or isolate the individual carrier frequencies up there, in this case AM radio. So we design a filter, and it can be either an odd number of bands, which means there's one centered on 0 frequency, or an even number, which means you don't have a band centered on 0. And first off, how can we have a frequency centered on 0? Well, in a software-defined radio, you take a chunk of the RF spectrum and you move it down centered on 0 frequency, positive and negative frequencies. It's a complex set of samples. And so this band would be centered on a capture. It's centered on 0 frequency of a capture of an RF frequency band. And I guess Miles knows that better than anybody, because you had comp theory, right? So that concept is not a foreign concept. It's just complex samples. But at any rate, so we define a band, and we're going to sculpt out a subband, and this is the scenario that I think we're using here entirely. I just incorporated this into my function so you could work even or odd. But the shape of this spectrum is going to be designed, the filter that creates that purple spectral shape is input as H-filt. Up at the top, you see H-filt, the second argument next to the complex data stream. So that H-filt are the filter coefficients that define some sort of a low-pass filter. So we only design a low-pass filter, and then because of the way the FFT works, this filter can be shifted around in the FFT domain and can serve as like a bandpass filter for all the other frequencies. So one filter design is all that's needed. It gets used over and over again to capture and shape the different subbands. And so it comes in as a long vector, and then it comes out as a long matrix. So it'll be a matrix that has so many, each row will contain a different subband. And we'll see the architecture that I set up for this. So we'll see this picture. This came out of the real-time DSP lecture notes, but we'll see a picture similar to this for the FFT next week. This is one of the cool applications you can do with the FFT. It's called transform domain filtering in general, and the specific implementation that depicted in this block diagram, which is part of the filter bank function, is called overlap and save. And what we're doing is we'll be using the FFT to do a convolution. So we'll do the convolution in the frequency domain by multiplying the spectra together. And the DTFT doesn't allow us to do that because that's infinite frequency resolution, involves a convolution like integral. But in the DFT domain, we can do multiply a finite number of samples in one of the input x times a finite number of samples of the filter function we want, and we can get the output, and then we can slide that along. So with the thinking back to convolution, when you convolve two, say, endpoint sequences, what do we get lengthwise? We get 2 endpoints minus 1, right? When we convolve, it stretches out the length because convolution introduces memory and it doubles the length. So what you do in the overlap and save method is you bring in 2 endpoints of the signal that you want to filter. You bring in a 2 endpoint FFT of a filter whose coefficients only occupy endpoints, not 2n. You have zeros padding this. This gets transformed, or in the case of the way that's going to work here, we'll do one transform and then we'll have the frequency coefficients, the DFT of the time domain filter coefficients. We'll have that sort of way it gets made use of in this overlap and save. But we take 2 endpoints, we got 2 endpoints here, we multiply them point by point, and then we're going to take it back to the time domain with a 2n inverse FFT. And because of the overlapping that goes on due to the action of the convolution, circular convolution in this case, which we'll learn about next week, not all the points are valid. We have time domain aliasing. You know, frequency domain aliasing we know about from sampling theory, but when you're thinking in the context of the DFT and the FFT, we have time domain aliasing. So some of the points, the first n points, are corrupted from the previous segment. So we harvest n points out of each of that step, but we're bringing our points in staggered by n points. So we have n new points put in each frame, and then we just harvest out the final n points, and then we put it back together. So just take a look at that and see if that's making sense. It won't matter to the project because you're just taking it for granted because I've already put it all together, but you see how it keeps up with itself though. Endpoints go in, but we pad it, and then we do this multiply and inverse transform, and then we harvest out endpoints. So n in, n out, we're in check. When I say in check, I mean we're real-time flow. We're flowing in n, getting out n new points. And you can change the filter on the fly. This overlap and save has got other applications other than a channelizer, but it's pretty cool. I like it. I mean, it's literally saying something that you learned about in signals and systems at the very beginning, working in the transform domain. You know, not worrying about a messy convolution integral, not worrying about inverse Fourier transform or anything like that. It's all done in discrete, hard, discrete time transform. So it realizes something that maybe a professor said is the dream, or maybe you dreamed about being able to do this. So one cool application that I've also been involved with is excising jammers. So it's really easy to set up excise a point. You can just set one of these DFT points to 0. When you multiply it times the transform of the segment, it's going to excise that bin if that was where a jammer or interferer was located. It's an excision. If you have multiples spread around, you could excise some of them out, and you would be carving out the spectrum of the input signal, and maybe that's not totally acceptable, but in terms of getting rid of the jammer, you would excise it out perfectly. Does that sound reasonable? You'd be doing it in the frequency domain. It's like you don't like this noise you're getting from this band, you're going to just excise it away. We're not doing that here, but we are going to do something interesting. I guess I won't say anything more about the channelizer per se, but I'll just, if yeah, I'll go back to this picture and just make another comment. The thing about this operation is if I take my filter in here, I will get a frequency response. It's padded with zeros. We'll see how that works next week as well. But now I have frequency sampled values of my filter design, a big FIR filter, a huge FIR filter, over 300 taps, very high resolution. But we can take these filter coefficients, which maybe correspond to a low-pass filter in here, and then what I can do in the transform domain is I can think about all of these filter coefficients, which are occupying minus fs over 2 up to plus fs over 2, and I can just roll those coefficients using NumPy's roll function, and I can roll it right to form another pass band and then filter again, roll it back twice, let's say, filter at a negative frequency, and so I can just roll it around and apply it in this multiplication. Does that grab you any way? It's like I do it once and I can just multiply, and then I've rolled a filter around it. One filter can be used many, many times to do different things. Now I know Emergent has a product, Arca Emergent has something. My former student is part of their channelizer. I don't know anything about it, so I can't say anything that it can or can't do, but they're doing fancier stuff than I am. But I got inspired because I looked at some papers. I didn't even know I'd be working for a company that has a channelizer product that they use for some of their customers. But there was another new function I wrote, complex ambiguity function. I wrote that, and it works in the same fashion as this, and it's also in SIGSYS now. The ambiguity function is used in radar-type applications, or it can be used in geolocation is one application where I've used the complex or the ambiguity function, where you're trying to correlate, you're trying to look for something in a waveform, not so much spread spectrum, but it just might be a reference waveform that you're looking for, like an application that I got exposed to, and I think I can safely say this, is where you might have a reference emitter on the ground, and it's broadcasting and it's seen by a number of satellites, and you can get that returned and then correlate with that known pattern that that reference emitter is sending, and then you can geolocate and do other pretty amazing things that are probably more secret or classified than, you know, I just know what you can do. I don't know specifically what projects use them, but the idea is it's similar to this, because instead of getting a correlation, remember we talked about correlation, that's one slice at a particular frequency offset. If you now use the same idea from this overlap and save transform, you can get the correlation at a different frequency offset, because these signals are going to have Doppler on them, and you don't necessarily know the Doppler because you don't know what satellite it's on or if something's in motion. So that's what the CAF function, complex ambiguity function, that's also in the same family. I wrote these two together, so I added them on. Okay, so here is an example of using it. This is just a warm-up exercise. This is in the notebook too. It's not a filter design that gets used for anything, but I just take and design using the Remez low-pass filter, a high-order low-pass filter, and then I'm going to generate noise across the full spectrum from minus fs over 2 to plus fs over 2. In this case, I'm setting the imaginary part equal to 0 on the input. I'm just saying it's a real signal. And then I'm going to set up the spacing to be 100 hertz, the FFT size to be 512, and the bands is an odd number. It's 2 times n bands plus 1, so it's 5 bands. This is very similar to what the first part of the design encompasses. And I'm just running that, and I'm getting my bank of outputs in W, and I'm just going to take the power spectral density of that, and this is a different function. It's not simple spectrum analyzer. This is another new function I wrote last year for this project, but it's in SIG-SYS. You're going to be using it in the homework set number 6 as well, which I've modified over what I had in the original notebook for chapter 6. We'll get into that later today. At any rate, so I take the power spectrum, and then I'm going to plot an overlay. So that's why I've got a for loop here. So in this case, that just shows you how simple it is to set up the channelizer. I'm just feeding in white noise, so all it's doing is just saying when the channelizer was sitting at this location, it looked like a bandpass filter at a negative frequency, minus 200 hertz, and then the next one is at centered at minus 100, so on. It doesn't sound very sophisticated, but it is in a way because it's using the FFT. So the parameters are the design of the low-pass filter, the spacing of the bands. The idea is you want them to mesh together. You don't want, but you could space them on purpose further apart if you wanted to. You don't want to have them really overlap. So I kind of did a design where notice they're kind of crossing each other at this point, which is down 60 dB. So we're not really getting too much leakage of adjacent bands from our equal ripple filter. The idea is, though, we're putting up a nice passband, rectangular passband, and we can pull something through. So this just demonstrates how you can do an even number. I just put this in here for completeness. We're not doing that in our application, though. So here's what the system block diagram looks like. We come in, since I don't want to reach up there anymore, I'm just going to show it from here. We come in with a capture from 470 to 1670. It's centered on 1070. So this complex baseband signal, I have taken care of centering it already. So the center of the spectrum of the capture on SLAC, 0 hertz corresponds to 1070. You'll have to keep that in mind, and this is in the example notebook and everything. So we're centered on 1070. Our sample rate is 1200 kilohertz at 1.2 megahertz. So we have a 5-band channelizer, just like what we looked at. We will take that 5-band channelizer, take its outputs, and decimate them by 5 because we don't need all of that sampling rate. We can just go back up here to this picture and say, if we decimate this band by 5, it's going to land right here. It's going to land at 0. In our grand scheme of things, we don't really care about aliasing because we just want to have it drop down to 0, and that will do that for us. We'll see that in the real-time example or in the audio example here in a second. So we can downsample at that point, and then in order to get the rest, in order to get everything else done, we're going to break it out into more channelizers that will channelize to 24 subbands each. So we'll have 5 more channelizers, and then from there we'll decimate by 30, and then we'll be down to an 8 kilohertz wide signal that can be fed into our audio playback. We can implement the detector for amplitude modulation, which is simply going to be an absolute value and a DC block. That's all it consists of. Miles remembers learning about the envelope detector, probably in AM radio, early in the class, right?
It's been a while.
Yeah,
So.
I get it. I can't forget these things, though. But I played with radio, with a crystal diode radio back in probably when I was in middle school or something. I mean, because of my household doing radio. So we have in theory, we have 120 channels that we'll be able to get our hands on. The DC block is just a simple high-pass filter that's thus and such. I'm not going to go into the modulation theory. That's for people that take Com 1 to really get into that. Just take it for granted that it works. It gets back our information. So these are the stations that Colorado Springs has. This is what the capture looks like, in particular when you recover the signal. I think I'm going to jump over to Jupiter right now, if it will let me. What happened? Do I have filters up or did it kill it? All right, where did it go? Yeah, why did it do this to me? This was working when I logged in, right? Where did everything go to? Let's see if it can find it. Have you ever get disconnected from Jupyter Lab before and had to reconnect from the browser? Has anybody ever experienced this?
I just got disconnected.
You did?
Yeah.
Okay.
But I think it's just we can
Okay. Well, see, what I did is I just guessed at the name. I know it's localhost 888 something or another, and I found it again. This saves you a step of having to take down the entire Jupyter Lab and then bring it back up again. So I've got Chapter 6, which I need for tonight, and I've got Project 2. So this is what the sample notebook looks like. Start it again. Okay. These are the PNGs that are in the zip package, just so you can have some graphics local. Here's the design we just went through with the low-pass filter experiment. I'm going to move beyond that. There's a section in the notebook where originally when I wrote this, I thought I'd have you do something with synthesizing your own AM radio stations, and then I trashed that idea. This was last year. I didn't take this cell out, so ignore this. I didn't write this in the version that's in the zip package, but I'm just telling you right now, this doesn't mean anything. You don't need to do anything with it. So now what we're going to do is we're going to load the capture file, and I can verify that the capture file is here. It's right up here. I loaded it in last night when I got it, something with it reworked. So this is AM3 FS 1200 FC 1070. It's encoded with this 3 means it's my third attempt at making a capture when I was working on this. And this cell sets the sampling rates all the way through, so these are like constants that will be needed all the way through. So the first thing I do is when I load this, I saved it in a Python NumPy binary zip format, the NPZ, NumPy zip. So what it does is it's kind of like if you've studied anything about Python with dictionaries, dictionaries have a key, and then once you have a key, you get access to the data associated with that key. So the NPZ file, it just says it's key AM3 underscore CPX. I put that in when I created it, and then to extract it, you have to load it with that key. So I'm going to load my capture, and then I'm going to pull that singleton key out of the load in this cell. So it's there, and you can look at this. Maybe you want to write it down. If you're having some problems with your download or something's not working, you can see that I've got 35,635,198 complex number samples. That's why it's so big. It's huge, and it's in float format, I think. I don't remember. I'm not going to mess with it right now, but you can do type on it or detype on it if you want to. Should we do that? Say I've done something. Actually, I can just do it this way. It's complex 128. So I did that for the wrong reason, probably. If I would have saved this as integers, complex integers, and then had you convert it to floats, it would have made the file a lot smaller. I'm putting in 32 samples, 64 sample, well, no, 128 bits per complex sample times 35 million. That's why it's so huge. Do you have an appreciation for why my file is so big? Because I know it was a lot smaller when I first got it off the SDR, but this is very wasteful. Nobody would do this except for me for a class project. I wanted to make it easy. And by the way, I didn't show this at the end, but look at the very end. I show you a picture of that's my hardware right there. I have a software-defined radio dongle that plugs into the USB, and then I have this thing called the Hammett up, which is an up converter, because the SDR doesn't capture signals down that low in frequency, so I shift everything up to a much higher frequency and then capture it there. And to capture it, I used a block diagram tool running on my virtual, on Windows 11, I'm running, now my brain's drawing a blank. I'm running not Windows, but I'm running Ubuntu as a virtual machine through Windows. So I'm running this application called GNU Radio Companion, and it has different types of widgets. And one widget or one block to put up is for the RTL SDR, set the sampling rate, and then set a file sync, capture a binary file, and then I later captured that to a different binary file format for Python. And then here I put up a widget that when I'm running the application puts up a real-time spectrum analyzer display so I could see what my antenna system was doing. So I'm in Windows subsystem for Linux G with the graphics capabilities, what I have running. I have it on this laptop too. It's running right here. If I bring this up, I dare not try to do anything too fancy with it because it's not, this laptop's just too old and weak, but I do have it in here. I'm going to let it rest. Save it for important stuff. Okay, so now we have it loaded. The first thing to do is to just take the massive array, just do a spectrum capture on it, and I set it to this mode false. And if I was to do help on here, what the false mode is for sinusoids. It scales better for sinusoids, so I just use that method for sinusoids in here. It's just a difference in the vertical scaling versus noise. So I'll capture that, and don't expect this to be lightning fast. 35 million floats. I mean, it's munching away here, and it's going to take a little bit of time. Okay, so there's our spectrum. There's some good strong signals. This was done at 10 p.m. at night, so there's lots of skip signals. And I explained a little bit in the reader part why I did this at night and what goes on at night. So the first thing to know about AM radio, it's been around for, 120 some years, I think. Maybe I don't have that right exactly, but it's been around a long time. Is that stations that first came up and got their FCC licenses got the right grandfathered in with them to have what's called a clear channel station. There's only 120 different spots for the entire country, so not all radio stations can stay broadcasting at full power through the night. What happens is the ionosphere shifts, the ions become more dense, so what's up there becomes more like a reflector for AM long wave being low frequency, can go up, bounce off, come down, so you can hear stations from all over the country on AM broadcasting. If you don't believe me, go in your car some night, maybe you have to get out of the garage, probably not, turn on your AM radio and just see what you can listen to. It's amazing. There's a lot of stuff out there. In this building, AM radio doesn't work too well because we're in a commercial building with studs. And what do you think studs do, metal studs do? It's like a screen room. We're in a screen room. The waves are so long, just think of that. The studs are close enough together that it looks like we're in a shielded room. So AM radio doesn't work very well. But in your wood frame house, it works great. I don't like that myself because I've had experiments relying on taping windows to the lab and stuff like that. But fundamental EM theory, though, why do microwaves have little tiny holes and we're still safe? Because we're blocking the L-band microwave signals too. At any rate, so these signals are from local and far away. Most of them are not discernible, but there's a lot of different spikes that I used. Notice that I used 2 to the 16th resolution in here because I wanted to make sure I could have enough frequency bins to get a resolution that would capture the plus and minus 10 kilohertz resolution. So at 1.2 megasamples per second, let's just do this and see where we're at. 2 to the 16th. This will be a basic property next week. When we go through the FFT, we have, so I'll put that in hertz. So we're down at 18 hertz. We have pretty good resolution for discerning signals that are spaced every 10 kilohertz. Okay, so let's just do a quick test. There's no part of the exercises that have you do this. Let's just do a single channel radio. So first off, I'm going to design some filters which work pretty well. You'll explore this in one of the parts of the project. Let's see what happened here. Did that run? I don't think so. There we go. These filters for stage 1, it's a 305 tap, and stage 2, 389 tap. I don't think there's any requirement that says you have to play around and try some new filters, but you certainly are free to do that if you want to. These get used all the way through too. So now I know that in particular my favorite stations are in Colorado Springs are these two, KRDO. You're familiar with their television version probably. Has anybody ever listened to KRDO AM radio? What do you listen to on them? Just curious. Talk or sports?
Sports.
Okay. I think KCSF does sports too, but I don't know. KVOR definitely does. I think they do which one does, out of Denver does Broncos, I think. I think you're going to listen to a station from Denver. I'm not positive if that's in the capture or not, but you'll figure that out. So what I'm going to do here is I'm going to do something very expensive. I'm going to go ahead and set up a 1300 hertz sinusoid, and I'm going to make that the difference between the center, 1070, that's my nominal 0 hertz, and I'm going to subtract from that 1300 and make that be a complex sinusoid at a negative frequency. So it's going to take a signal that's up there at 1300 and move it down to 0. So maybe my motion here is not super great, but I could probably try to draw a picture on here or just visualize it again. If it's in the center right here, and we're going from 640 to 16, whatever, 1300 is going to be up here. So we want to bring 1300 down. So we're going to have to multiply it by a negative frequency to shift the frequency down. And you could check this out and see if that's what I'm doing here. Then I'm going to apply the low pass filter to capture that in, and then I'm going to decimate by 5. So this is our basic multi-rate sampling, just done on a grander scale. This takes a little bit of time. And that's done. So now the next stage is to downsample it. And now that we've got it at 0 hertz already, I'm just going to set a low-pass stage 2 low-pass filter. And this, in effect, is going to be very similar to what we would do if we were, I don't have the results in here. Go back over to this. Well, here's a picture of it right here. Basically, what we've done is, by another means, we've gotten the signal to land in this green band right here by moving it over and filtering it with the stage 1 filter. So it's kind of that shape like you see in green there. And then I'm going to downsample it by 30 this time. So here I'm taking it down by 30, and that 30 is going to take us the rest of the way down. It's going to take us from 2, let's just go through that for a little emphasis. We're going to go from 1200, we divided by 5, and we're at 240. Now we're going to divide by 30, 8 kilohertz. And we can play an 8 kilohertz stream through the audio subsystem of the PC. So we're down to 8 kilosamples. Not a little bit of shrinkage. We're not going to be plus or minus 10 kilohertz. We're going to be plus or minus 8 kilohertz into that neighborhood there. Good enough for our purposes, though. So I'll do that here. And this will run faster because why? Why did this run faster than the first one? Just checking your sanity. We started off at 1200 kilohertz, right? Decimated by 5. And we had to process all of those 35 million samples. But now that we've decimated by 5, we reduced the number of samples by a factor of 5, right? So now we can process that vector much faster. And now we're decimated by 30, so we're way shorter. So now at this point, I'll just take a look at what we're doing. And this was just to look at one signal, and we're zoomed way in on it. So this is plus and minus 4 kilohertz. So that's amplitude modulation. There's characteristic of AM is it's got a carrier, pure carrier sent with it, and that's what the spike is here. And then it's got nominally, perfect theory, symmetrical sidebands. So it's not quite true, but that's the way it was put on at the transmitter at least. So now we can come through and take the absolute value and then apply the DC block. And that's the way the envelope detector is going to work. It's going to get the envelope fluctuations with the magnitude of the signal, the ABS, because it is still a complex waveform. And then it's going to be writing out a DC bias, so we remove the DC bias with this filter. And let's just take a look at it. I don't know if that looks like audio to you, but those would be indicative of syllables of somebody speaking, right? Long and short syllables with breaths and things in between. Of course, nothing would be complete without listening to it. So now we're just going to use audio, which, remember, is imported at the beginning. And audio has a number of options, but you can just simply put in a vector that you want to listen to and then simply set its sampling rate. It doesn't have to be saved as a WAV file or anything. You can just play it. It made this picture, and let's just run it through here.
6, and then the Niners at 5 and 7. So the Niners at 5 and 7 have a chance to make the playoffs, where the Cowboys at 5 and 7 do not.
Notice there's other stations in there.
I mean, they do.
You hear more than one?
Because the records, if you just look at the conference, if you look at the
What do you
records,
think causes that? I said clear channel. Signals are going back and forth. Local stations can broadcast, but they have to reduce their power. But that doesn't mean that other states nearby aren't broadcasting and they're lower power and still skipping greater distance. So very often, I'm not positive, but I would say those are just other stations that occupy that same spot, but they're in a different state or who knows where they're from. Interesting. I mean, I had the radio bug from a very young age, so listening to radio, my father doing amateur radio, to me that's a normal sound to hear doubling. Another phenomenon is going to show up, and that is we have some intermodulation, which I talk about in the reader document, where strong signals can intermodulate with weaker signals or another strong signal and form a product. And it might be to form intermodulation that lands in the band, you have to do like 2 times 1 minus another signal, frequency-wise. Does that make sense? If you take 2 times 1 signal's carrier and subtract a different carrier that's still in the AM broadcast band, it will show up somewhere else in the AM broadcast band. That's called a third-order intermodulation product. You can have 5th order and 7th order. They can all land back in the band again. Now, unless you do radio design, you don't really think about these things, but these things were studied ages and ages ago, so-called intermodulation issues where it happens. Audio, it can happen too, but it's going to sound, in our ears, it's going to be different, but in radio, intermodulation from overdriving some analog stage can be devastating. I say devastating because it just messes things up badly. So there we go with that. Then here is just an example of doing the same thing, except now we're going to go with a full band. So we're going to start with the 5-band system, and that's just with noise going through it, and this is going to capture the required bandwidth here. This will take longer. This will be the second stage. No, I guess this is the first stage too. Now I'm processing the real channel through there, so this is going to take longer. I forgot the order of these things. Remember, the dark circle means it's busy. So you got to wait for it to get clear. Please don't get impatient, because all you're going to do is back up more tasks, and it could cause your system to crash or Jupyter Notebook. This is very helpful. You don't see this in, I don't think in VS Code version, but in the full Jupyter Notebook, that little display that tells you that it's still running lets you know to just stand by and wait. Okay, it's done. So now we're going to plot the overlay of 5. And again, this is still very long. We haven't decimated yet, so we're doing 5 of them. I had all of this pre-built, but then I wasn't going to have to rerun it, but my computer restarted, so we're now going to wait again. Okay, there we go. So now we're seeing the stations, and the station we were listening to, if you're wondering, is the one at 1300. It's the one right up here. I know, you don't know, but part of what you're going to do with this exercise is not be quite as engineering, super technical. You're just going to be more of a, implementer or a user type person. So you're going to just get familiar with what's going on. So that's in subband. The subbands are labeled according to Python indices, so 0, 1, 2, 3, 4, and the way I see it, you can take a listen to anything you see in here. I don't believe there's anything in band 3 or band 2, so that's why I just listed 0, 1, 3, and 4. So you'll be drilling in a little bit to each one of those in this exercise and just scoping out what you're finding in there. And you might find some intermod products and other interesting things. So now we'll do stage 2. Stage 2, I'm going to increase the resolution to 2048. And the number of bands is 23. It's still an odd number. Remember, it's 2 times n bands plus 1. So, and let's see, what did I do? Yeah, it's already been decimated by whatever the factor was, and that number was put in up here. Based on the number of bands, that sets, as I'm remembering, sets the decimation factor. So these are already shorter in length, so this should run faster. So this will be a noise test. So there's the 22 bands, just putting in some white noise of variance 1. That's just a confidence builder. Put something in, just make sure it's functioning properly. And now we're going to pass the real test through. $35 million is just a lot, but imagine working, and I've had to do some things. I mean, you work in radio, you get a lot of samples. Okay, it's done. Now I'll take a look at it. And I didn't tell you which band I was grabbing either, so I'll tell you that as soon as we get this out. Yeah, subband 3. So how did I indicate subband 3 is right here. I'm getting my input by taking the bank and taking row number 3, and then the colon to take all the columns. Does that make sense? You're experts at Python now, we're indexing. So there it is. It's now got to compute 23 spectra, even though it's been decimated. This is probably the longest one. There it is. Okay, so there's the station we were listening to, and everything looks pretty good. You're probably saying, how is it that we're seeing some adjacent channel interference? Remember the crossover points of the filters, how many dB down was it? It's about 60. So that means it's possible, and it's an equal ripple filter. So the equal ripple filter is flat in the pass band, and then it just drops down and it stays flat. So anything that would show up anywhere would fold back in, down 60 dB. So this one is coming some green and some yellow. So maybe it's from here. I don't know. Don't super sweat it, but just understand though, if you were on any engineering project, you always have to have an understanding. I mean, in general, when I first saw that, I had to think about it for a while. I mean, who wouldn't want to think about it? If you're a lazy engineer, you'd say, oh, it's not a problem, and then all of a sudden in front of the boss or something bad is happening. So I definitely thought about it and wanted to know where it was coming from. So there it is, and they're sitting roughly in the center, so it should just be a matter of picking out whatever row that we're in after the second stage of subband filtering, and we'll get our signal back. Make sense? So what utilities did I put in here to help with that? First off, I have a function at the top which I didn't really explain, but it has to do with the fact that because we're using powers of 2 FFTs, we can't get exact spacings at 10 kilohertz. We're going to get close, but not dead on. And when I created this, I thought that would be okay, and then I turned that into a problem. So I let you investigate that. It's not a major thing. What you'll end up doing is you'll say, okay, Dr. Wickert says, if we use a power of 2, we're not going to get exact spacings. And we'll have a little bit of error, like 1199.8 corresponds to 1200. Does that seem like a big mistuning in the radio if you were thinking of tuning a dial or something? Probably not very bad, but so I investigated that a little bit, and you'll investigate it a little bit. The answer is going to be you're going to try putting in not a power of 2 for the FFT, and you're going to know after next week that it's going to maybe take longer, but if it gets you a more accurate result, it's all going to depend upon some other design aspect of it. But it's very easy in simulation to just put that in because the NumPy function will handle it, and you'll be able to get out numbers that match. So, and as you're going through this, I'm always trying to display the number of the actual RF capture. So I'll take a frequency that I get internal, I'll add 1070 to it because that's where it was centered originally, and then depending upon the subband I'm in, which is spaced on 240 kilohertz, I add that number gets added in. So you'll see little fudge factors in there. So as you're looking at this, try to unravel that, what's going on there. I was really good at it when I wrote it. You know, I spent a year not playing with it. Why did I do that? I have to stare at it again. I think you'll be able to figure it out, though. So that's that part. So here, what I can do is I have, like I said, a little utility freak to IDX. So what the idea was, I'm counting from 0 up to 22 across the band. How do I know where 1300 is, what index it is, if I wanted to listen to 1300, or if I wanted to listen to 1240. So I have this little tool. I just said, I want to listen to one of those 3 frequencies, 1210, 1240, because I was interested in this one. I wanted to know if that was anything. I knew that looked like it was 1240, and that definitely looks like 1300. So I just put those into my little utility, which is defined at the top, and then it pumped out, that's index 1, 4, and 10. I mean, you'd be able to say, Miles would be able to say, if they start at 0, that's got to be index 1. You could just put your finger, count across, and you'd be able to figure out the index. So let's just put in index 10, which according to this little calculation is going to be our 1300. So I have that loaded in right here. Or if you want to hear it, one of the other stations, I'm not going to do it twice. Which one do you want to hear? You heard the 1300 before. Okay, and that's index 4, is that right? Okay, we'll put in index 4 into here. And you can see the back end is, I'm just going to get that one vector out, I'm done, and then I'm just going to do the absolute value and then the DC block, and then I'll have some speech, and I will listen to it.
Saving it for my house, and I was looking for guidance because first time buying, I have no idea where I'm going. I've almost got my 20%, and that's where I'm at. Good for you. What do you do for a living? Honestly. I just had some control. Good for you. So, how much have you got saved?
It sounds like two stations on the
So, I've got 26,000, and I'll have the rest of it by mid-Jan.
Okay. I didn't remember that. I thought it was more discernible. I guess because I was doing some testing and wanted to create some KRDO signals. I don't know. I could create a new test vector, but I know when it was worked by one student last fall, that student got the right experience out of it, and I think you'll get the right experience out of it. You want to get done with the semester. I don't want you to feel cheated, and I know I'm giving you plenty of opportunity to do something interesting. So just go for it and see what you can make out of it. You're kind of like intelligence people. You're gathering intelligence, and you can learn some things from it. So what you do from here to answer the questions, you just carry on. I basically have the code cells in here that lets you do the exercises you might, and then at the very end you'll tweak the FFT length and verify that, and then you'll send me, I ask you to send me 2 WAV files of what you consider to be your favorite signals, and I will listen to them to verify that you got them out. How do you create WAV files? ss.toWave. So once you have a vector, like it will be the one that we listen to down here, x1300 record, you'll just go into this function and you can just, let's see, fingers on the wrong button. Give it a name with the single tick marks, give it the rate of 8,000, which was one of the sampling rates defined at the beginning, then give it the test vector, and you'll see it show up in your folder. You can double click on it, you'll be able to listen to it locally, and you'll be able to get it, no problem. Okay, I've spent a lot of time on this, but it's probably my trademark. I want to be thorough, and I want to give you the right go-ahead to feel comfortable going after this. I know you're going to get it done early if you put the time on it. If you don't put time on it until after you take the exam, it won't take that long. It doesn't take that long. Any questions? Does it sound interesting, or does it, if you don't like radio, I don't know. I guess you could be in DSP and still not like radio. But I find it interesting. I like using tools that I learn about to go after some things that maybe I'm interested in, and maybe you've been interested in that. This could apply to anything. And an RTL SDR dongle is about $20. Still, the higher end ones are maybe 30. They're a lot of fun to play with if you do the comm lab, which Miles, you didn't do the comm lab, but they do get played with in the comm lab. So I had a question, or not? You didn't have a question?
Oh, yeah.
You were stretching?
The lab before that one is the 32IDX.
Mm-hmm.
Is that defined somewhere?
Yeah, I said it's at the top of the notebook. Let's go find it. There it is right there. I have an MO, right, how I operate, so I've done that kind of thing before. So now I guess we can take the break and come back and roll on the topology stuff, which is, it's going to take some time, and I'm going to have to keep my tempo up, but it's pretty easy going down. I mean, the last 2 weeks, you'll be able to drink it up and get to work. The homework's easy too. I give you a lot of options on the homework. You might have noticed, if you haven't, that I have bonus points. I have minimum, like pick 3 of 6 or something like that, whatever it is. I'm just trying to give you the opportunity to try some ideas out, and then the only thing that I haven't posted up besides grades and scores and things like that, I will have a review sheet that we'll go through next week, and that will finalize kind of my intents for the final exam. Based on where I'm at, when I finish the lecture on the FFT chapter, DFT chapter, then I'll be able to say in my mind what I'm going to do. I have the ability to say, no, you won't have that. If you have this, it'll only be this and that type of thing. And I just wait till I'm in that mode to know exactly what it's going to be. I'm not going to write an exam where we don't cover something and that you're going to be kind of feeling bad about it. Sound good? Okay. I'm going to eat some of my lunch I didn't get to eat when I was driving. So I'm going to pause this. Okay, we're going to go back over to the notes now, and I'll be ready with my notebook here, and I'm going to push this notebook up. I made a few changes in it today before I went off to my appointment up in Denver, so I'll push this one up, and we'll talk about it for sure. So what do we want to do in Chapter 6 is we want to look at structures for discrete time systems, and start with block diagram representations. And as I said 2 weeks ago, we'll go through signal flow graphs. And then we'll be looking, after we do that, we'll be looking at finite precision. And in the homework, for example, you will be doing something with quantization in FIR systems. It's a pretty simple example, and it's kind of interesting to work with it. I was going to introduce you with more. I did already have you do something with fixed point math, though, in Python directly, and you got to do that smoothing filter. And maybe I'll just, since we're going to start talking about quantization eventually, but it's on my mind right now, did anybody notice anything that changed when you went from the float version to the fixed point version? I haven't looked at your solutions yet to know.
One of them is slightly more accurate. I think.
Yeah, I think it's slightly more
I
accurate.
can't remember.
Did you zoom in on it and see how grainy it looked on the,
It's like green.
because of the fixed point range, it was in one integer at a time. It was just hovering as it was going over that smoothing trajectory. It was just hovering and very discreetly. It was obvious that it was doing that. That'd be the quantization noise that we talked about earlier. But other than that, I mean, I had to do something similar in a project at work where we had a smoothing filter, and it wasn't really that big of a deal. The FPGA designers, developers, they were doing it in fixed point, and my only concern was, are we scaling it into a big enough integer range that that quantization is not that noticeable? I mean, they maybe wanted to be down lower, and I would rather have it been up higher, because that way you have bigger dynamic range and each step is smaller. Each integer step is smaller when you get up to a bigger range. But it should have added a little bit more into the mean squared error. Not very much though, right? Or at least for me it didn't. Yeah, but it was higher. If it wouldn't have been higher, I would have been disappointed actually, because there has to be some price to pay for fixed point math. So in the beginning, the block diagrams look like this. We're either merging two signals together, or we're putting a multiplication along a branch. Those are the basic operations. And then the third operation is just a unit sample delay. And tend to want to have this in block diagrams, because then it denotes the complexity involved, rather than, you wouldn't put a z to the minus 10 in there like you would in Chapter 5, where you just want to say, I'm going to delay by 10 samples. In a filter and topology chapter, you'd want to denote, how many delay blocks are there, so you know what the storage space has to be. The biggest thing that goes on here, and I didn't pull out my pencil, I guess I'll just go without it for right now. A big change that occurs in this chapter, and this is very, very big, so I want you to make note of this. The difference equation changes, so now rather than these terms originally, when we first talked about difference equations, they were sitting over here with y of n. So when they get moved in this chapter to be on this side of the equal sign, The minus sign that should have gone with them is now absorbed inside. So just make note of that fact. There's a minus sign that's now going to be present inside of there in those coefficients. And when you have to draw some other topologies and things, and this is it right here. It's sitting right in there. And if I was to rearrange this, I would move this side up to the left-hand side, and then when I move it back, it would become positive. So that means the AKs are going to have a sign change. If I was writing this book, I don't think I would have done that, but I'm reading the book just like you are. So just be careful, and it'll be a threat to your making a typo or an error in the final, of course, too. So we can implement this difference equation, and this is the equation that will be used to implement in what's called a direct form 1 structure. So this is an nth order difference equation, direct form 1. And all it's doing is, if I was to put these on the same page, like that, you'd be able to see that our output is composed of present and past values of the input, and that's all of this left-hand side here. You can just see the B coefficients and the delay blocks, and then we'd also sum in the past values of the output with their weights. And so if you had to, convert this back to another design, you may have to, visualize the minus signs that are actually been absorbed in there. So that's called direct form 1. And then if you rework the block diagram, if you take the block diagram that we have right here, and you were to say, let's take this half of the diagram, let's move it on to the left, and that's kind of what this difference equation is showing. We're going to rearrange the difference equation so that we can do the feedbacks first and the feed forward second. So we actually have, in this notation, we have two systems. We have the feed forward part and the feedback part. So in this picture up here, I just simply show you how you could, first of all, put the feedbacks first, which is the upper diagram, feed forward second, and then I look at this as like a spinal column of delays. That's remember my socks and other analogies. This is the analogy that the delay blocks are like vertebrae in your spinal column, and now they can be shared. So when you create a direct form 2, you get to share, and you have less delay elements required to do the implementation. And that's a direct form 2 is pretty popular for that. We'll also have transformed direct form 2, but this is just a slight change in topology. Now, given that the multiplications are perfect, and that's what they are in this block diagram because we're not indicating any fixed point processing, and the coefficients are stored with all the resolution that they need, there is no difference because we're using linearity to make this change, right? With linearity, we're allowed to change the order. Just as long as we do the same algorithmic steps, we're okay. But in a real implementation with finite precision, even float precision that's finite, in effect, we do have differences between these two. But for homework problems and things, yeah, you can rearrange them. So direct form 1, direct form 2. The book has some trivial little examples, and its trivial examples I don't much care for because they're just trying to get you the concept, but they're making it pretty straightforward. Here's a direct form 1. Here's the difference equation. Let's just emphasize that. In the difference equation, notice that 1.25 down here is now a plus, and the plus 0.8 is now the minus 0.8. So just make sure you track that out. But this would be a direct form 1, feed forwards, feedbacks, and then rearranging it into direct form 2 is the second one. Now we'll just carry on with the signal flow graph idea after it gets talked about here. Signal flow graph is no different than the block diagram. It's just a more compact, more streamlined form. And like I was saying 2 weeks ago, I got exposed to it in microwave circuit design when you're doing microwave interfaces with forward and reverse or reflected waves, and in control systems, it comes up. But maybe, John, you'd say that Dr. Platt doesn't spend any time on SFGs and flow graphs.
He mentioned them. I mean, he does a lot of flow graphs, but not, he's like, you can do SFGs also, but he doesn't do them.
He doesn't call it out.
Yeah, I mean, he did call it out once, but he likes doing more blocky type of thing.
I know he likes Simulink, or at least he used to use Simulink a lot.
He does like doing that.
Yeah. He told me he'd probably never learn Python, but that was quite a few years ago when I was talking to him about it. That's okay. I'm a signal processing person, so I think I felt inclined to want to learn the other languages. I wanted to be versatile in the other stuff. But at any rate, the signal flow graph is just a more streamlined version, and it's network or graph theory is what you get into. And I had to take graph theory as a graduate class at Michigan Tech because they didn't have any other graduate courses one semester, and my advisor just said, you're going to take this class because it's all that's offered. So I learned about graph theory, cut sets, and other things that I barely remember, but it was fairly interesting at the time. So the signal flow graph is directed branches, and that is what makes signal flow graph theory special for signal processing controls and microwave circuits. Things do not flow in two directions like they would in a schematic for a circuit. I mean, when you think about a mesh or nodal analysis in circuits, current flows any which way, right? It's a wire that's just can flow on. In a flow graph, it goes the direction of the arrow. So the arrowhead points in the direction of the signal flow. Nodes are either sink nodes or source nodes. So a source node just means that we can tap as many things off of the source node and they can go in whatever directions we want to go in. And when we go to the other end where we have a sink here, or we have sinks in I guess where else do we have a sink? We have a sink in here. Those two are coming in. And what type of node is this node right here? This is a hybrid sort of, but it's more of a source node. C comes in, and B, A, and E are all flowing out of it. I wouldn't call it a source node, but it's a different. It's not a sink node. So you just have to obey the rules of the signal flow graph, and if you put a z to the -1 or anything next to a branch, that means that it's going to be that anything in terms of the function. It's going to perform as the signal flows through. So z to the -1 just means the signal gets delayed by one sample. Now we'll be able to take a signal flow graph and convert it to its Z-transform equivalent, and that is quite easily done. We'll show that in an example here in a second. So this is a first order signal flow graph, and this should look like which of the two? It should look like direct form 2, right? Because you just think about how it's set up. Direct form 1 means feed forwards on this side, feedbacks on this side. So here we see the feedback first and a feed forward second, so it must be direct form 2. Now we are going to have transposed direct form 1 and direct form 2, which are not to be confused with, direct form 1 and direct form 2. So the transposition It's just going to be slightly different. So what you can do with this, though, just to get your mind thinking on it, you can redraw, replace the nodes that are acting as summing junctions right here, summing junction, that branch and this branch come in together. So replace the plus sign here, replace the summing node junction over here, and then the box C to the minus 1 with the C to the minus 1 along the flow. And then at this point, if you're having to write out equations, which you have to do in the homework a little bit, and likely in an exam question, it's best to put some labels in. So like W1 of N will be the signal that's at 1. This is more like circuit theory where you're thinking of node voltages. So you're just thinking of labeling something as it's a node sequence. Just label them, and then you can go ahead here and just write them all down if you feel you need to do that. Now, if the objective is to get the output in terms of the input, suppose this was not a recognizable form like a direct form 1 or direct form 2, then yeah, you have to write all these down and then decide how you're going to write the output in terms of the input as a difference equation, because that's what you're expecting to find, right? You're expecting a signal flow graph is going to define a difference equation that relates two nodes together. And if you're writing this in VHDL or writing it in C code and you didn't have a direct form algorithm already available to you in a subroutine or something like that, you'd have to write a sequence of ordered calculations to get the operation complete. And this is where I mentioned 2 weeks ago also that you don't see any of this. You see somebody's code, and then you try to figure out what is this code doing, and you have to unravel a signal flow graph from it and then understand, you know, what are the coefficients that control the poles and the zeros and so on. So my preference is to start with these and then get a handle on it, making some substitutions like seeing W2 as W1, and it's this right-hand side, and then have Y is equal to W3, it's also equal to W2, and W2 shifted. At this point, you can't move forward in the time domain because you're in kind of a chicken and the egg problem. You can't really write out the difference equation very easily if you just try to stay like this. You want to get Y in terms of X, which is way over here, and you can make some substitutions, but this is going to be a roadblock for you. So what you do now is you do just like we did at the end of chapter 2, you can take the Z transform of both sides of difference equations, and then you can spin things around. So that's what I did here. I wrote W2 of Z, and then I rearranged it. So I had the W2s pulled to the left side and then factored out. And then I did the same thing on the Y equation where I factored out the W2 and the Z to the minus 1. Then finally I could stick them together by making the substitution for W2 in terms of X of Z, and then finally you've got it. And then you know from chapter 2 how to get difference equation. Make sense? Does it seem worthless? I mean, you might think this is just an exercise in math, but I don't think it is, because you're going to see, like I said, code from somebody, or you may have to help somebody with the code, or you may, like me, working with the FPGA developers, they're just a different breed of people, and you have to be able to work together with them. I mean, I'm not saying they're bad, it's just that they think one way and we think another way, and we have to come to terms and check their work, because if they implemented something, they said, yeah, that's what you told me, and you went back and checked their code and came up with a difference equation saying, no, I don't think you did, because I don't see it doing the same thing in simulation, and I don't agree. So you have to be able to obviously work together. And I don't want to sound like I'm in a campaign to win a war or something. You do have to stand your ground, though, and work it out. So this is a good example, though, of one I told you 2 weeks ago. It's called a lattice structure, and a lattice has a crisscross in it usually. And this one, you wouldn't know what it is. So you're given this structure, and you can then proceed. And I'm not going to dwell on this, given that we don't have that much time, but I wrote it out, and then I switched everything to the Z domain, figuring that that was going to give me the right insight to be able to make all my substitutions and eventually write Y in terms of X. And so I just started, progressively eliminating. And I'm not fond of giving these on exams because everybody thinks differently. Everybody will do something different. They'll either get it right or they'll get it wrong. I mean, there's only two things that I see, the right way or the wrong way. So if I decide to give you this type of problem, I hope you can get from one point to the next. So here I just, like I said, I eliminated, and you just have to see it yourself, just like when you did circuit theory. And I don't know how you feel about that. You're saying, I'm beyond that, I don't need to do that again, but you have to do it here. So eventually it works itself down to an amazing filter that we've seen before. Where have we seen this before? In chapter 5. That was the all-pass filter, right? With a real alpha coefficient. So what makes this topology special for all-pass filters is there's only one alpha coefficient in there. You don't have to worry about it being represented more than once or having a minus sign on it, which might change the precision or something because of the sign change. So this is good for all-pass sections, this type of filter, this type of topology. So there's a direct form 2 equivalent that does have the two coefficients in it, whereas the lattice structure only has the one. So now that we've been through that, now we'll talk about IIR systems, infinite impulse response systems, and some of the issues that they have. So this I got from information over the past 30 years, so it's not necessarily all in the proper order, but factors that come up with topologies is computational complexity, such as number of constant multipliers, number of storage registers. I was taught in the beginning that was all that mattered. They were always interested in how many multiplies you'd have to have. And then the next thing would be how many storage registers. That still is burned into my brain, but then VLSI comes along and people say you have to think about chip area, modularity, and data transfer simplicity. I've not taken VLSI design, but I certainly played around. I took analog IC design, and I've laid out PCBs before too, a lot. And I know that layout is a big thing in terms of interfaces and connections and things of that sort. So there's different rules that apply. I know what the FPGA people use. I don't know what the ASIC people use necessarily, but I'm guessing that they're somewhat similar. You have probably libraries and modules, or Xilinx calls them IP, intellectual property cores and things that you can use. But if it's a simple design, you probably are better off just integrating it on your own with the gates that are the logic cells that are available. At least, again, I've seen that from FPGA developers before, that they just use the raw parts that are available. They don't necessarily instantiate a core or something like that unless they need to. Anybody want to offer any comments from classes you've taken, whether that's true or not true? And then if it's a multiprocessor system, partitioning, communications, that's stuff that I'm certainly aware of, and I certainly come up with some of the things I've worked on where they need lots of processing power. Remember the Arduino I was talking about, the Arduino Q that came out. I bought one of those. I've been playing with it whenever I have some time the last month or so, and it's got inter-process communications, things that you can do. You write Python on the embedded processor, which is a Dragonfly from Qualcomm. It's a Qualcomm chip. It's got 853 cores on it. It's running Linux, and you can talk to it directly, or you can talk to it through the Arduino interface. And then it's got a microprocessor on the board too, which is its second controller chip, which is a ARM M33, I think, from ST Micro. And that you program using the original Arduino C++ language, but you can intercommunicate, and you can do some other pretty cool things. I'm no master at it. I've just tinkered with it. It's kind of fun. It's kind of like a Raspberry Pi in a way, except it's a little bit nicer because you've got two different engines on it that are very connected together, and you've got a coding environment that they give you that ties it all together. Everything's under one umbrella. But it's very, very much in its early adoption stages, so there's not a lot written about it. Okay, finite register length effects. This is where we get into the quantization side of things. What do we decide to do with coefficients? How we're going to store them in registers on the machine, or in the fabric if it's FPGA. And how you're going to quantize it. So we have that to deal with, and that's what the last part of the homework for set number 6 deals with. This is the big realization that I came to, and I've already mentioned this, that network with a minimum number of multipliers and delay elements may not be, in addition to what I said about implementation these days, may not be the least sensitive to finite precision arithmetic. Something that's so efficient on multiplies and so efficient on delay elements might be more sensitive to coefficient quantization because it's so wrapped up in itself. This is just a review of what the flow graphs look like for what we've already talked about. So here's direct form 1, and this just counts off what the requirements are: multiplications, additions, buffer storage, and coefficient storage. Here's direct form 2. It's got slightly different numbers. It's more efficient for buffer space because it's sharing the common backbone. Simple example again. I'm not going to go through this example at all, but this is just a signal flow graph version, kind of like what we did before. And you can use this to track your minus signs. So just fix your eyes on this when you start looking at it, saying, yep, all these signs are flipped back when you're putting it in here, so they get pulled out accordingly. So watch that when you're working the one homework problem. A third type of topology is cascade form, and cascade form is just cascading second-order sections that are in the numerator and denominator. This is used in the real-time DSP lab, and John, you got exposed to this quite a while back probably, but you definitely used the cascade idea, and that's talked about in the notebook too. So you factor it into second-order sections, and you can have single first-order sections if you want to, but generally you just merge these together so you have a common architecture of a second-order section when you multiply it out and keep your coefficients real then. So, and that's what this bullet talks about, forming second-order sections. So it's a biquadratic, and this is what the cascade of second-order sections looks like. If you're doing this in FPGA, you can cascade these together in Fabric. If you're doing them on, say, a processor like the ARM Cortex-M4 that you used in the lab, it just runs one, and then it takes a sample output from the first one, resets the coefficients to the initial conditions of that stage in the cascade, and runs it again, and loops it on itself. So you have state maintenance that goes on in a typical cascade of biquads if you're going to recycle them, like in the Cortex-M examples in the lab. There's many different orderings, and how you order them. There's a little comment on how you do that in the quantization section, but there's a lot of different orderings that you can do. There's NS factorial square, different pairings to start with, but MATLAB's toolbox, Python's toolbox makes recommendations and orders them in a friendly fashion. So here's what it would look like in a cascade. You would have one filter following the other, and then you would have this set cascade, or this biquad, running these 4 steps, or having these 4 different attributes: multiplies, additions, the amount of RAM, the amount of ROM that's required. The ROM is the storage of the coefficients, and the RAM is, I guess, what am I looking at here again? I'm trying to remember the additions. Data RAM. There's 5 coefficients. Data RAM is the elements that are needed to store the intermediate calculations. That's what that is. So it's all of these points where 2 nodes come together. You have to store an intermediate calculation before it moves on, or at least that's where they're counting it in here. It seems like you wouldn't necessarily need to do that. I'm saying 1, 2, 3, 4, 5. So I guess that's where that's coming from. Some of the homework talks about how you can simplify things and think things through when it asks you questions. There's things you can simplify. So this is the difference equation it takes to do your biquad section. So this is in the C code for the lab, where you're coming in and you're going to run the first difference equation to do, in this case, a direct form 2. So you're going to do the feedback section first. Then you take its output, which is a WK, and that drives the feed forward section, which is the second difference equation. And then in the case of the C code, at least, it has to store all the states, which are what are stored in these WK elements. These states are the ones that correspond to your delay coefficients, because those apply uniquely to that element in the cascade. You remember, John, you remember this, but nobody else wrote code, but it manages itself, because I wrote a function, and ARM has a library called the CMSys Cortex-M library for DSP. It has library functions that manage all this stuff with a state variable, matrix, and then a coefficient array, or coefficient matrix, I guess, for the cascade. When you get into finite precision effects, people look at how to simplify things here. One multiply is pulled outside so that you can reduce the number of multiplies on the inside over this first calculation. The B0K can pull out. The thing about a cascade, though, is that you have to worry about whether or not you need distributed scaling. If you had fixed point in here, you'd have to worry about having overflows at intermediate stages, so you might have to apply some intermediate scaling. I got involved with that in a big way, and not for filters, but for the whole subsystem I was working on for the spread spectrum radio I was part of, and I suggested different scaling approaches to the FPGA developer. I modeled it in Python, and I came up with what I thought was a good solution. He came up with his solution. I said, it's not the same as mine, but if it works, we're going to go with your solution, because I'm not going to insist. I mean, it worked, and his idea changed some lookup tables we had to create, because it was slightly different values than what I was using with my scaling approach, or my distributed scaling approach, but in the end, that also worked. So here's just taking a single biquad section, and this is a really silly problem in the book, because it just breaks it into 2 first-order, cascade of two first-order sections, which is just kind of silly. It's just kind of an exercise, though, to say, hey, we could cascade 2 first-order sections as long as they're not complex conjugates, because then you'd have complex coefficients. But so we'll look in Python, see how it sets it up. This form we're not going to spend any time on, so this exists, but it doesn't really have a practical use the way I see it in most modern day implementations. You'd use partial fraction expansion and you would break everything up into a parallel form that looks like this, and in block diagram form it looks like this as a signal flow graph. You still have biquadratic sections, but you now put everything in parallel. It's an interesting concept. It does give you robustness to coefficient quantization. Like the cascade idea too is also better. The direct form structure is probably the worst because it's building up one big polynomial, and if you have a little bit of quantization in the coefficient, it's going to make a bigger error than if you have the smaller chunks of quadratic sections. But this just doesn't lend itself to the same implementation flexibility, I don't think, and I have not seen anybody actually use it. But I put an example for completeness, but I didn't give you any homework problems on this. So last thing here is, before we move into the FIR, is feedback loops in both types of systems. So this is just sort of a silly thing, but it's something that is worth talking about, and that is whenever you build an infinite impulse response system, you've always got something that's going to recurse infinitely, and that's what's going on here. So you have the potentiality for instability whenever you have a recursion going on, and all IIR systems have that. What are some options in dealing with that? Well, you use it as you need to use it, but of course, what do we know about for this first order loop? What's the stability requirement on this simple first order difference equation? Magnitude of A has to be less than 1, right? That was our way back in chapter 2. So that's the stability requirement, and if you're quantizing your coefficients, you have to make sure you don't quantize some number rounded up to 1, because that would be a bad thing. That would turn a stable system into an unstable one. Here's an interesting example that the book has. It just says, here's my signal flow graph. How did I get it? I don't know. It was given to me. Study it. So you break it down, and you realize you can factor the numerator, and then you can do a cancellation. So that's gone, and it's now just a simple FIR feed-forward system. So why would you do this implementation? I think this example was thrown here just to say that you can kind of lose sense of reality and go off and build something that you don't need to build. Why build it recursively, and why have the added complexity there? Then there's another type of loop, and this is something I learned about when I first used Simulink a long time ago, a very long time ago. You can put up a flow diagram or a block diagram, and you can create what's called a non-computable system, because you end up having what I think Simulink used to call an algebraic loop, where you don't have a loop that's got a feedback delay of some sort in it. And that's what this example is. This is called non-computable, because if you write out this loop, you see that you have y is equal to a times y of n plus x of n, and you say, well, how can I compute that? I don't know what y is, because that's what I'm computing. And of course, the algebraic thing to do is just rearrange it. So you can say, it's like you're slapping yourself on the side of the head saying, you dummy. I didn't need to do that. All I have to do is put in a 1 over a scale factor. So I'm pretty sure Simulink, if you give it a block diagram and it has an algebraic loop in it like this, it will fix itself on its own. I haven't used it in such a long time, but I remember it used to do that. Have you bumped into this in controls?
I'm not in the controls lab, so
Okay.
I have to use Simulink.
Okay. So the bottom, there was an early simulation package that I wrote a book of examples for called System View, which is now part of the Keysight portfolio of software simulators, that would not let you even put an algebraic loop in. If you drew your block diagram, and that's how it worked with block diagrams, and you put an algebraic loop in, it would put in a z to the minus 1 delay there automatically. It didn't even ask you, it just did it. And that, of course, changed the system function. So I had to learn a little bit about how that worked. That was the developer's way of making sure they don't build something that's unstable. So before we go to the final little steps here, we'll look at transposed signal flow graphs. This is just a property of signal flow graphs, and it's nice in DSP in particular because it says you can get at you can get 2 more signal flow graph fundamental types. What the signal flow graph transposition theorem says is that a transposed signal flow graph is one where you reverse the input and the output, and you reverse the directions of all the arrows, and then you've got a network that behaves identical to the original one in ideal theory. So a book I used to teach out of by Jackson had a proof of it using a state variable technique to prove that signal flow graph transposition is true or works. So here's what it is. You just take your flow graph like this, and this could be on an exam problem, it could be on one of the homework problems. You just simply take this network, and the way I like to think of it is you just take it, it's like here it is on the paper, you just flip it over, and then Y is now the input, and X is the output, and the arrows, you just change the direction of all the arrows, they flow in the opposite direction. So this is just flipping it over and leaving it as it was originally, but now we're going to, then you flip the arrows around. So I guess I did flip that around. I did it twice. So this basic flow graph transposition idea leads to what's called transposed direct form 2, which is this one right here. This is the one MATLAB uses for its filter function. This is also what NumPy uses for, or SciPy.signal uses for its L filter function. It uses a transposed direct form 2. So notice how a few minutes ago we were looking at a direct form 1 and a direct form 2. So what does this look most like to you if you look at it? Does it look like a direct form 1 or does it look like a direct form 2? It looks like a 2. Why?
I mean, it looks like it because it has the delays. But
It's got the backbone for one thing.
Yeah.
But it's going up instead of down.
Yeah, it has to be forward first. So.
Which is like 1. So
Direct form 2 structure.
it is a direct form 2. You just have to decide whether you put this on the front of it or not. Is that what you're saying?
No, it's because you're asking a question, it just doesn't answer.
Yeah. I'm just kind of teasing a little bit because I know what are common errors on homework or exam questions. I'm just trying to make you smart on this a little bit. And I'm just the professor, so I want you to get it right on the exam. If you want to forget about it after that, that's okay too, because you can look it up. But, I mean, again, though, this is something that could come up in deciphering somebody's code, right? What did they do? What is this thing that they just did in the code? I think I tried that in an exam problem a couple times. I'm not sure I'm ever going to do that again because it is kind of tricky to study it in code and then decide how to figure it out. But this gives you added flexibility. I mean, the guy that implements the code or the FPGA fabric, whatever, they know what they're doing. But then a while down the timeline, it's like, what did I do there? I don't know. You should document what you did. You should put some comments in your code that say, what did you do? You implemented it as a direct form 2 or something. So this is a transposed direct form 2. And when we look at FFTs next week, you can take a flow graph for a fast Fourier transform and you can transpose it too. So you'll get either a decimation in time algorithm we'll talk about next week, or decimation and frequency. One is just the transpose of the other. So for FIR systems, there's not nearly as much to talk about. They are always feed forward, because that's what an FIR is. It's just a matter of, do you want it to look like this arrangement where you've got the delay line, as I refer to it. This sort of looks like a microwave circuit kind of a topology where you've got z to the minus ones, like a transmission line tapped off at different instances, but it's a digital signal flow graph, and then you come down and sum all the values coming down through the filter weights up at the output. So this has the tap delay line across the top, and then our transpose of that creates the second topology where it sums up all the samples, or it takes the samples and distributes them into all the filter coefficients, and then brings them up to the delay points and lets them combine together there. And then people have said, okay, suppose we have a linear phase FIR filter. Did I talk about the seatbelt filter project thing that I discussed? I worked for Ford Microelectronics, and they used to be in town. I taught a short course up there, and they were talking to me about how they decide when they blow the airbag on the accelerometer. So they have a high order FIR filter. This was in that day, and they may have changed it, but they had a high order FIR filter, and they wanted to implement it more efficiently. And I suggested that they use, if they're doing it in linear phase FIR, that they could use this idea here, where you just fold the filter on itself using the symmetry, whether it's type 1, type 2, or type 3, or type 4, and you get something that looks like this, where you're going to reduce the number of multiplies by 2, and then sum them up along the bottom, and have the delay line, which we had in the FIR direct form 1, running just folded right here. So that's why it's called the folded FIR. So the first and the last join together, come down through H0, and so on down the line. And in this case, there is no center tap, but if you change it to an even number of, or an even order filter, then you have an odd number of taps. So that's, yeah, never mind. That's what this example is. This has an odd number of taps, because here we don't bring two coefficients together. We just have a single center tap right here. This part goes away if you have an even number of coefficients. So where did this come up in the seatbelt problem? I took a much different interest in the problem than they did. They're the implementers, the IC designers and things. My interest was really, how do you arrive at this, and how many cars get destroyed when you're figuring out what filter you need to make? And they didn't give me a very clear answer on that, but my understanding that I learned from working on this a little bit was that they try not to destroy too many cars because it's expensive. Does that make sense? But yet, you know, I told you my experience a block from my house, how somebody ran the four-way stop. Airbag blew off, and it was just like somebody fired off a shotgun inside my car. And it smelled like somebody fired off a shotgun too. It was a pretty eerie experience for me to have that happen. So they have to, bottom line I'm saying there is, they have to make a decision, and you have to decide when to do it. And I got injured by what flew up at my chest. I mean, the seatbelt, and I got the seatbelt injury because I got jerked around across my chest and got a little bit of contusions on my rib cage from it. That I think is part of the compromise in living through an accident, though, right? That I think we all know can happen. I don't know what they did exactly, but coming up with the filter coefficients has to be some experiment with accelerometer and other things. That'd probably be an interesting thing to work on, though. I don't know. You'd probably do some things in a lab, work with accelerometers, do some things with forces and something outdoors, and then eventually mount everything up in a car and start doing things with it there. This is the other type that doesn't have the center tab, the type 2 or type 4. Okay, now I'm just down to an example that I have of doing it in Python, an IIR design, and I'm going to switch over to the notebook for this example, I think. So I'm not going to really look at any more at that one. MATLAB, when I used to use it, it has its signal processing toolbox, which I think, I'm guessing that you use this in 3205. Maybe, maybe not.
I don't think we use that tool.
Okay. The FDA tool. I know they came up with something else after it, but I haven't used it for over 10 years. I mean, so I don't really know. We have what's in Python, and I'm pretty happy with it. What the MATLAB toolbox allows you to do is visualize more in a more interesting way the cascade idea. So here you get a cascade response using its function, and Python has this too, and that's what I'm really going to look at in the notebook here very quickly. But what's my big thing was a three-dimensional plot that FDA tool could create for a cascade of second-order sections. You could see how there's 2, 4, 6, so that's a sixth-order filter. So here's what each biquadratic section is implementing for this elliptic filter. And you can, I guess, never mind, this is a fourth-order filter. There's two sections, and then a composite. So that kind of gives you a better idea, though, of how the second-order sections visualizes itself. I know I could work something out in Python if I had to. I just put a picture of that in here because I was impressed by that back in my early days. So we're going to look at finite precision, but before we do that, we're going to jump over to the notebook. So here, I have to run this again. So here I'm just playing with IIR Design Helper, which is what I put into my Scikit DSP-Com. It's functions that are available in scipy.signal, but I just rewrap them into an interface that I found useful for the DSP lab. I think I have you use these in the lab. I did that in a very deliberate way because I wanted to create a function that could give you the A and B, which is part of the direct form implementation we just talked about, but it also sends out the SOS, second order sections is what SOS stands for here. So here I did 4 different designs of Butterworth, Chebyshev type 1, Chebyshev type 2, and then elliptic. And I designed all 4 of those right here using the IIR Design Helper. And then I'll just run that so I get them loaded. Well, actually I didn't run this yet. So I just can break out and look at what is SOS1, which is SOSC1, Chebyshev type 1. We can look at the coefficients. The coefficients are organized so that each submatrix is composed, or each row of this array. The first row is the first section with the numerator coefficients across the top and the denominator coefficients second, and then the next cascade element is here and here. Third one is here and here, and the fourth one is here and here. So this was a, if I go look at the length of B sub B, or A sub B, I mean. What does the denominator look like for its 14th order? Oh, I looked at the wrong one. I needed to look at Chebyshev type 1. Butterworth is longer, but Chebyshev type 1 should be the 4th order, or 9. So what do I have going on here? 1, 2, 3, 4. 2 times 4 is 8. So that means one of these sections is only a 1st order. Is that right? I'm not seeing it myself. See, everybody know what I'm doing? I'm looking to see that I've got a quadratic. And well, how do I get 9? 9? Oh, wait a minute. Never mind, that's right. The number of coefficients in the direct form 1 is 9 because it's an 8th order polynomial, right? 1 less, there's a constant coefficient, so 9 coefficients corresponds to an 8th order polynomial. So I have exactly 8 sections in this. And I got the dimensions of the SOS matrix right here. It's 8 by 8 because wait a minute. No, I'm confused again. 8, 8. I only see 6 across the top. Why do I see 8? Oh, never mind. That's the number of poles and zeros. I'm getting tired. That's not SOSC1. This is the C plane, and then the number of poles and zeros. Let me just run it. So this is a special version of Z plane for second order sections that takes advantage of the fact that the roots are much easier to calculate for the second order sections, and SciPy.signal has a support function for that I took advantage of. So this is very accurate routing because it's only a second order section. You know, there's 4 second order sections, so they're very easy to do the quadratic equation to get the exact roots. And these roots are all supposed to be at z is equal to -1. And if I tried doing this in a direct form 1 or direct form 2, I'm probably going to notice that these might not be quite so perfect looking. They're going to still get counted as a repeat of 8 zeros, but they might have a little bit of change because of the rooting function. Won't get it quite right. I'll just kind of leave that off to the side for now. So here I use frequency response cascade list, which we got introduced to earlier for FIR, but now I'm doing it for IIR. So this way I can just kind of do a filter design and compare. And here I put the number of poles in each of the filter types. So it depends on what you're after. If you're after the shortest length filter, the elliptical is the most efficient. That's something that you learn. I talk about this more in my old real-time DSP class. It's just a property of filters, whether they be analog or digital. The elliptic is the optimal for getting a transition from the pass band to the stop band and with the least number of poles. Remember that? Maybe Dr. Trimboli talks about that.
I'm pretty sure he did.
I know I talk about it in the lab notes for sure, but it depends on what you want to have. We could debate that, but the Butterworth has the obvious advantage that this just continues to asymptotically go down because it doesn't allow for any ripple in the stop band. And the Butterworth has the added advantage that it's very, very flat in the pass band. It has no ripple at all. So you get what you pay for. Extra poles give you extra cushiness in the design. So here I took just a little example. SciPy.signal also has, in addition to L-filter, they have this function that works with the SOS filter. So this is just available if you happen to have an IIR filter where you have the SOS expansion for it. So here I just did that. And I just put a sinusoid through and then added some noise onto it. And here is what I'm wanting to replace what's up above here, which is in the existing notebook that I'm going to replace tonight on the website. I'm replacing it with my new PSD function, and I'm setting it to false here. And to get an idea, let's just do this so you can see what the noise calibration does. When I put it in the noise mode, what it's doing, which is for the second one, which is the orange one, I think, PY, yeah. This raises it up higher because this is trying to just reflect the noise power correctly in terms of spectral density, whereas if I go with the, switch this back again, the sinusoidal display, I'm trying to make this value here in dB represent the actual dB value of a sinusoid that has an amplitude of 1. So it should be, in the power spectrum, it's going to be down 6 dB, and that's 10 right there, so 6 is right up here. So I did that so I get an approximate value from the spectrum of more like what a spectrum analyzer might do. So that's the difference between the noise and which is true and false for the sinusoid. My voice is just getting dry. It's not sore right now. So now we're going to go look at quantization. So jump back over here to the notes. We're heading into the home stretch right now. One of the main motivations for looking at different types of topologies is to know what sort of sensitivities they have for finite precision effects. I mean, obviously you choose them for reasons more than just finite precision effects, but you have to think about, what you can get away with. Maybe you get away with less bits with one topology versus another, so that's obviously a consideration for implementation in FPGA and in hardware. So we have to think about number representations, coefficient quantization, quantization noise effects, scaling, and then the very end, which I probably am not going to get to, this idea of the limit cycles. The limit cycle is just where you've got some sort of feedback loop, and the fixed point arithmetic means that you get a ticking action in the filter. That's a very unacceptable behavior, and on my project this past fall, I was worried about that at one point. I said, did you possibly implement a limit cycle? And the FPGA developers I was working with knew what I was talking about, because apparently they have seen it before and they're aware of it. So it's just sort of an interesting phenomena with feedback present in fixed point arithmetic. So again, the number of representations we talked about in Chapter 4 when we were talking about quantizers and things. We have the same idea. The most popular fixed point is 2's complement, but the binary point is generally sent one bit to the right of the word, the binary word here. So the fractional part is B1 through B sub B, and B0 is called the sign bit. This is the traditional way. This is what we did in Chapter 4. That's what the notes does here. It talks about the standard 1 bit of precision, or 1 sign bit, and then the fractional bits. This is what we've gone through before, but at the very end of this, I'm just going to mention, not right now, but when I get there, that multiple sign bits is also another option that designers use these days. And I got exposed to that on my FPGA project this past semester. So I'm going to point some resources out. I had hoped to develop a notebook. If I don't want to grade papers, I might develop a notebook. I don't know, because I've gone down this path for work and a little bit here. I just didn't finish it off. But at any rate, this is like what we've seen before. Two's complement, rounding is the most common. That's where we have a tread and the stair step. This is the less common, the truncation approach. So we're focusing, in the homework problem at least, on the rounding. So rounding means that if we get an overflow, we will wrap. And that's what's called natural overflow, I think. Yeah, overflow. And that's just because two's complement numbers, when they reach the positive, they go all the way back to the negative and work up again, or they go the opposite direction. If you're getting two negative, they will wrap back to the positive. And it's devastating. This is what it looks like if you wrap around. Whereas if you have saturation, and generally in arithmetic, like on microcontrollers and things, you get to set whether or not you want to saturate or whether or not you want to round. Usually the rounding is turned on by default, is the default setting, which is the more devastating of the two. Saturation is just a clipping, just saturating into the top or the ceiling, above or below. So let's kind of look at how this plays out in a system briefly. This just looks at our C to D, which we've dealt with before, our D to C, but then we have a simple first order IIR filter in the middle of all this. So what we're kind of homing in on is we have two things going on right here that are new to us. We have the multiplication. Then we have the coefficient itself. So the first part is representing the coefficient quantization. We don't get to put A in there, we put A hat in here. And that's the focus of the homework problem in set number 6. But then globally, we have a multiplication of, say, a 16-bit coefficient times a 16-bit signal sample that's flowing through there. We multiply, it grows up to 32 bits, and then it has to get truncated back down again. And you got to experience a little bit of that in the project problem, right? I mean, if I ask you to testify, I did get some exposure to it. I'd never taught that before because I didn't run into that until this past fall. Early in the fall, I experienced it working with the developers on the FPGA, and I probably got more excited about it than they did. Why? You ask. It's a good question to ask. Because as an engineer, as you're going through your life as an engineer, when you bump into something you've never seen before, it's kind of like when you're in school, you learn all this stuff, but you go ahead and you're going to see things you've never seen before, and it's kind of exciting. It's kind of thrilling. It's like, wow, I never learned this in school. I gotta try to understand this better. So I'm not saying you should be smiling about it yet, but you will have those moments where it's like, hey, I just learned something. So what does that make you? It makes you a little bit more valuable probably to your employer because you've had some added experiences to your life. So quantization, representation, so that's what's shown right in here. But then to flesh out the model more, we have, we might have a quantizer as we come out of the D to A or A to D converter. So we might reduce the number of bits present. So we'd have a quantization model. And then the multiplier that's present in here, that's the coefficient times the signal flow. That's another quantizer. And then finally, we might take our output out to yet a different quantization level. So this is the true nonlinear model, which these days people would tend to do in Python or whatever language they're working in. In the olden days, they'd go back to the linear additive noise model and put in the coefficient values as quantized, and then just spread around the additive noise models as needed from the way we did things in Chapter 4. And I think you got exposed to that. Another good question, I realize I'm meeting up seconds. The exam 2 problem with the quantizer, I haven't looked at your papers enough to know, did you get very comparable results with that model or not? That's problem number 3, I think. You don't remember? I put that problem together because it's kind of like, I want you to see that you can model things pretty accurately. If you really set your mind to it, you can get an accurate model. And to me, it was kind of like satisfaction, and I do that in my work too, because I like to do modeling and I like to improve upon modeling approaches. So, but this is a good picture to just show you what you could go on if you had to go with a linear model. This is would be the more common simulation approach. So, coefficient quantization is what the homework problem is about. This is just showing you for IIR systems. Really don't have time to spend on this, but it's just saying that each coefficient here is going to get quantized, and it's going to have a sensitivity associated with it. And this was an analysis technique that just says if you have a little bit of, if you have, say, a situation like this where you have poles clustered here and here, and you're thinking about our model where we, move around on this unit circle to get the frequency response, what happens if those poles and zeros get shifted ever so slightly? It's going to change the magnitudes, and it's going to put ripple in the response. So that gets talked about in this IIR example. This was done in floating point versus fixed point. This is something that people came up with a long time ago that just said, hey, standard direct form structure does pretty crappy. If you try to quantize to fixed point arithmetic, you don't get a lot of good selections down here near the real axis. So this topology, look what it does, uniform, amazing. I mean, I'm just saying, and I know you're wanting to get out of here. So in the FIR filter, I'm going to jump right over to Python. We just want to change one coefficient. There's some extra things, no homework problems, no exam problems on it. So let's just look at the Python for a moment. So we have our simple quant function that you've already been exposed to. So let's see, I guess you got to install this or load it. This just shows you what happens if you let overflow take place. It's definitely wrapping. This is not very many bits, though. It's only 4 bits, so. And I set the quantization levels. But here's what you do in the homework problems. You design a filter. And this is a little bit of a trick question, but it is in the homework problem, so I'm still hanging out here a bit. What's the maximum coefficient? 0.3369. So you have to worry about quantization of coefficients that are approaching 1 in this case. I'm sitting at less than 1/2, so I've actually got an extra bit of precision hanging out in here. Would you say that? I'm only at 0.3. 0.5 could be my largest value in my coefficient array. I wouldn't have to set it up to 1. But I set it up to 1 right in here, X max. And so I quantize it to 14 bits, compare it to the unquantized filter, and not cool. I mean, you can see the effects of the quantization. What would happen if I did that, because I know I'm not exceeding that with my coefficients, right? It got better, right? I know you're wanting to get out of here, but these are the types of things you can explore so easily. I did a model of quantization noise that hasn't been tested out. FXP filters. I had that up and that lost on my computer. I'm not going to go find it again, but that's a package for Python that I played around with. I promised that we'd get through it, but that was before I wrote the smoothing filter problem. So you've had some exposure. I may put some links up to this since they got erased on me. I don't want to go looking for them, but I'm pretty sure if I was to go look for it, it's probably in here. And there it is. Of course, I'm not going to stay on the internet very easily. I put that package on my system, but I don't have time. FXP Matho is one that I reviewed, and it's one that you can look into if you ever go this way. But look how old I am. I didn't run into this stuff until the last year or so. And I'm excited about it still because of the fact that I learned something new. I didn't have an option. You know, that's one of the things about being an engineer. You're confronted with a problem. How do you get out of the problem? Quit? That's not the honorable way. You just have to go solve the problem. Well, okay, find a senior person in your group and ping their brain and see if they can help you with the problem. So, any questions?
Do you have a date and time frame?
I have the time that's on the schedule.
17th or 16th?
Oh, okay. Question is on the final time. It's on the 16th, and I think John looked it up, right? 5:20 to 7:20.
I found in the school schedule that's from fall 2024. Are we still following the same schedule?
No, you can find the one.
I'll look it up, though. Send me a reminder. Just Slack message me right now, and I'll make sure I get it up there. I'll put it on the home page. The only way I can make it at a different time is find out what's going on in this classroom. I know there's a class that meets in here ahead of us. I would love to come over here earlier or later. I mean, give me some of your thoughts. We found this time because this worked for everybody, so it is in the early half of our session, right? No, it isn't.
It's 5:20 to 7.
Yeah, it's shifted a little bit. Is everybody okay with that time, or is there an issue? Because I can start trying, but okay. If we started at 4:45, though, would that be better, based on your habits?
Sure. Yeah.
That would be better.
I don't really care that much.
Okay. Well, I'll spend a few moments thinking about it.